This lecture investigates the consequences of missing variables in a linear regression model. The setup for this lecture is as follows. We have a random sample and a linear regression model. Any variable that really ought to be included in the linear regression model but is not is called a missing variable. There are several reasons for missing variables. One could be that even though we realize that a variable will affect our y variable, we simply do not have the data. For example, I might expect that the intelligence of a student will affect the result on the final exam, but I might only have information such as the number of hours the student spent on the course and so on. Another reason could be that we have the data, but we simply don't believe that an explanatory variable affects the y variable, so we don't include it for that reason. In the same example, I might have other data such as the gender of the student, but perhaps I believe that the gender doesn't affect the result on the final exam, so I leave it out. It could also be that a variable I have included actually has a non-linear effect on y, so I should really include perhaps the square of the variable as well, but I have not. All those are examples of missing variables. Variables not in my regression, which really ought to be in my regression. So what we want to do in this lecture is really to figure out the consequences of missing variables. And to do that, we again consider the simplest example we can think of, and that's an example where I have data on a y variable and just one explanatory variable. I might have data on a second explanatory variable x3, but I don't use this data. So I run a regression of y on only x2. So suppose that this relationship holds. The expected value of y given x2 and x3 actually depends on both x2 and x3. And let's assume that it is a linear relationship between them. For example, y could be the result on the final exam, x2 the number of hours that the student studies, and x3, well, perhaps it could be the number of hours that the student exercises. And the assumption here is that both these variables will affect the expected final result. However, I actually believe that it's only the number of hours that the student studies that affects the final result. So I do not include x3 in my regression. However, since it does affect the expected value of y, it should be included, so x3 is here an example of a missing variable. So let's look at a simulation study that illustrates this example. Here I have data on x2 and x3. I have simulated an error term, and the data generating process for y is that y is determined as beta 1 plus beta 2 x2 plus beta 3 x3 plus the error term, just like the linear regression model. And the case here is that the intercept is 0, beta 1 and beta 2 are both 1. So the expected value of y does depend on both x2 and x3. Here I run the correct regression model with no missing variable. So I run the regression y on both x2 and x3. And down here I have done the missing variable case. I have just run y on x2. So let's look at the consequences now of a missing variable. first, this is the setup in general. LRM, I have at least one missing variable. I assume that the Gauss-Markov assumption holds for all the variables, meaning that if I had included the missing variables, I would get consistent and unbiased estimators, and OLS would be efficient. That's the assumption here. For example, that assumption is satisfied in the simulation because I have simulated the error term such that it has expected value 0 and a constant variance equal to zero point 0.5 squared. So I know for a fact that these three are unbiased and consistent, and I know that these are the efficient estimators. I cannot find an unbiased estimator which is linear in y and which has a lower variance. Now what we want to do is to investigate the properties of these ones when we fail to include x3 in our model. So here's the bad news. If you fail to include an explanatory variable in your model that should be included, then the OLS estimators will in general be biased and inconsistent. That means that when you estimate your beta parameters, then your estimator is not correct on average. It may give you an estimate which on average is smaller than the true value, or it's larger than the true value. Even further, even if you had an infinite number of observations, you would still not be able to get the correct beta parameter. So that's the inconsistency. Since you have inconsistent and biased estimators, all types of inference based on the OLS estimators will be incorrect. The confidence intervals will be incorrect. If you test an hypothesis and you set alpha to 5%, it's not going to be 5%. To add insult to injury, even the standard errors are inconsistent. So if you are missing variables, if you suspect that you're missing variables, then you need to be very careful with your interpretation of your estimates. So here's the good news. If the included variables are independent of all the missing variables, then the Gauss-Markov will still hold for your regression model and OLS will work perfectly fine. All the estimators will be unbiased and consistent. The standard errors will be consistent. The OLS will be efficient. You get correct inference and so on. And you can probably guess that since it's the case that everything works fine if the missing variables are independent of the included ones, and it doesn't work in general, you can probably buy the fact that the higher the correlation between the included and missing variables, the worse the bias and the inconsistency. So excluding a variable that's highly correlated with an included variable will create quite a severe bias and inconsistency. So let's confirm these results with the simulation study. Here is the covariance between x2 and x3. Right now the covariance is 0, and I've created a simulation in such a way that when the covariance is 0, they're actually also independent. In this case, the missing variable problem is not a problem. Our OLS estimator will be unbiased and consistent. We can check the unbiasedness by looking at this coefficient and redoing the simulation. The true value of beta 2 is 1, So B2 should on average be 1 if I redo the study, and you can see that it does indeed look like it's on average 1. You can see that the standard error tend to be higher in the case with missing variables than with no missing variable, and that's not too surprising because if I run a regression with only y on x2, the x3 variable will go into the error term. So I'm simply increasing the variance of the error term and thereby increasing the standard errors a little bit also. However, if we make x2 and x3 dependent, then the estimator with missing variable will suffer. Let's make it 0.6, the covariance. Let's have a look at B2. That's the estimator of beta 2. Let's check if this is on average 1. So I'm F9ing, and you can see that it's definitely not unbiased. It turns out to be greater than 1 each and every time. It looks like the expected value is somewhere around 1.6 rather than 1. So B2 is now biased. Another slightly interesting thing we can see in this simulation study is that if I take up the covariance to 0.99, I can only take it up to 1 in the simulation study, so that you can see that x2 and x3 are really highly correlated, almost the same for each observation. Then the bias of my B2 will increase. The expected value looks to be somewhere around 2, twice as big as the correct value of 1, but in this case it's actually better than the one where x3 is included. In this case, the missing variable estimator comes out to be better than the correct specification. You can see that with the correct specification I get like -3, and I get really horrible results, 7.2 in this case. And that's of course due to the multicollinearity problem. We have almost perfect multicollinearity, so that the variance of the OLS estimator is so high, making the estimate basically useless. So we need to elaborate a little bit more on this missing variable problem so that you don't go away with the wrong understanding of missing variables. So here is my, let's call it my correct specification. It includes both of my explanatory variables, x2 and x3. Here is my model where I have only included x2. I have named the error term in my model epsilon I with a superscript m, just to remind me that that's not the same error term as in the correct specification. You can actually see by just comparing these two that the error term in my model is actually the correct error term plus beta 3 x3. So what's happening here is that this x3 variable gets included in the error term of my model. So in this lecture we concluded that if x3 is correlated with x2, then the missing variable model has a problem, because the OLS estimator will not be unbiased and it will not be consistent. But we have to be a little bit careful with this interpretation, because otherwise you may actually conclude that you should never run this regression. And you may end up concluding that all information from this regression is incorrect. Well, that is actually not true. So remember how we interpret the beta parameters. If we go to the correct model, the interpretation of beta 2 in the correct model is how much will this part change if I increase x2 by 1 unit. It's the derivative of this blob with respect to x2. Remember, partial derivatives are always interpreted this way. That is, if I increase x2 by 1 unit and I make no changes to x3, what's the effect of this blob? Well, this blob is really the expected value of y conditionally on x2 and x3. So what beta 2 tells us is what is the partial derivative of this blob with respect to x2. So when we say that in our model B2 is a biased estimator, we mean that it's a biased estimator of this interpretation of beta 2. So it is a biased estimator of this one. If I run my regression model with missing x3 and I try to interpret my estimator B2 as what is the effect of increasing x2 by 1 unit, keeping x3 constant, then my answer will be biased. However, B2 in my model, it's not a biased estimator of this one, where we just control for x2. So if I rephrase my question as follows, I run my regression model, I interpret B2 as the estimator of the increase in y when x2 increases by 1 unit, and I am not trying to keep x3 fixed, then my estimator is no longer biased. In terms of the simulation study, then yes, this estimator is definitely a biased estimator of beta 2, because beta 2 is the derivative of the conditional expectation of y given both x2 and x3. But again, it is not a biased estimator of the effect of x2 on the expected value of y if we allow x3 to change. You can see in this example that with this interpretation you should get a number which is greater than 1. If you increase x2 by 1 unit, then since x2 and x3 are correlated positively, x3 tends to increase as well. Not trying to hold x3 fixed, you can show that in this example x3 will increase by approximately 0.6 units, this number here. So B2 measures really the combined effect. x2 increases by 1 unit, that will increase y by 1 unit. As x2 increases by 1 unit, x3 increases by approximately 0.6, and that will increase y by an additional 0.6 unit. So in total, an increase in x2 by 1 will increase the expected value of y by 1.6. So in that sense, it is definitely not wrong to run this regression model, even though you know that you have a missing variable. As long as you are really careful in interpreting your B2. You cannot interpret it as the effect of x2 keeping x3 constant. You can interpret it as the effect of expected value of y increasing x2 and allowing x3 to do its thing. Now this line of argument actually explains why OLS works if you have a missing variable if x2 and x3 are independent. Remember, if I take this down to 0, making x2 and x3 independent, then suddenly this one becomes unbiased. Why? Well, because of the following argument. I increase x2 by 1 unit. That on its own will increase expected value of y by approximately 1 unit. I allow x3 to change, but in this case, they are independent. So if I increase x2 by 1 unit, on average, nothing happens to x3. So there will be no additional effect on y, and that's why the total increase in expected value of y will stay at 1, making B2 unbiased and consistent, and in this case an unbiased and consistent estimator of this one, well, as well as this one in this case. They will be the same. You can extend this line of reasoning even further. Suppose that I'm leaving this example now, I have a linear regression model like this, beta 2 xi2. Like this, I have a bunch of explanatory variables. Let's say that this linear regression model is also linear in data. We know in this case that beta j for an arbitrary j between 2 and k, not for the intercept, is the partial expected value of y conditionally on all the x variables with respect to x2. And let's try to consider this question. Is beta j in general a marginal effect of xj? And let's add the word true here. A true marginal effect of xj. And by that I mean, does beta j answer the question, what happens to the expected value of y when I increase xj by 1 unit and I keep everything else at the same level? Not just the x variables in my regression model, but everything. That's really what we mean by the marginal effect. Well, we know for a fact that beta j is this expression. So it does answer the question, what happens to the expected value of y if I increase xj by 1 unit, keeping all the explanatory variables in my regression constant? That is answered by beta j. And let's fix this 2 to a j to make it correct as well. But the marginal effect really wants to go further. It wants to keep everything else constant. So it really depends on what we have accumulated in our error term. So you can think of this as containing a whole bunch of additional x variables. So the question is, am I really allowed to claim that beta j measures the effect if I keep all x variables, including the ones in the error term, constant? And now we know the answer to that. The answer is yes. If the x variables in the error term, if all those ones are independent of the x variables in my regression, these ones, then the answer is yes. Because in that case, if I increase xj by 1 unit, nothing will happen on average with the x variables in the error term, and I can interpret my beta j as a true marginal effect. The effect of increasing xj by 1 unit, keeping everything in the rest of the world constant. The answer is no, otherwise. If something in the error term is affected by a change in x2, then beta 2 is not a true marginal effect. It's still this one though. You still have this option. You can still view it as the increase in expected value of y if x2 increases by 1 unit and I keep the x variables in the regression constant.